This is your presenter Asloob Mudassar, and I am presenting slide number 87 of the course on laser physics. Question is, assume that a resonator consists of two mirrors with radii of curvatures R1 and R2 separated by a distance capital L. The geometry is shown in figure 87.1. The beam wastes have been indicated. Find out the indicated beam wastes in terms of the parameters of the cavity. Also assume that the cavity satisfies the stability condition. So let me first discuss the figure. The caption of the figure is indication of a beam waste in and outside a two-mirror resonant cavity. So you see that this resonant cavity consists of two spherical mirrors, spherical mirror 1 and spherical mirror 2. The two mirrors are separated by a distance equal to capital L. The radii of curvature of these spherical mirrors are R1 and R2 respectively. The beam wastes have been shown at three different places. That is at the location of the spherical mirror 1 represented by 2W1, at the spherical mirror 2 represented by 2W2, and the diameter of the beam waste in the within the cavity is represented by the 2W0. Our objective is to calculate 2W1, 2W0 and 2W2. And we have been given the condition that the system satisfies the stability condition. That is, the cavity is stable. So let's try to answer this question. Answer. Consider a two-mirror resonator as shown in figure 1 with its lens guide geometry shown in figure 2. The lens guide geometry equivalent to the figure 1 is shown in figure 2. We shall be coming to this one in a minute. Assume that the field at the mirror 1 is known, which propagates towards the mirror 2. After reflection from mirror 2, the field will return to mirror 1. After one complete round trip, the field can be calculated if the complex beam parameter Q is known. And you know that Q is actually the complex radius of curvature. The detail about the value of Q or the parameter Q has been discussed in the previous slide, that is in slide number 86. So now let me show you the figure number 2, discuss the figure number 2. This figure number 2 is actually a lens guide geometry, which is equivalent to the geometry shown in figure 1. So this is the mirror geometry and this is the equivalent lens guide geometry, which consists of two mirrors, plane mirror 1 and plane mirror 2. And just in front of these mirrors, there are two lenses. Lens number 1 in front of mirror number 1 and lens number 2 in front of mirror number 2. The focal length of these two lenses, that is at mirror number 1 and at mirror number 2, is F1 is equal to R1 and F2 is equal to R2, where F1 is the focal length of the lens 1 and F2 is the focal length of the lens 2. And the beam wastes are the same that we have shown in figure number 1. 2W1 is the beam waste at the location of the mirror 1 and 2W2 is the beam waste at the location of the mirror 2 and 2W0 is the beam waste within a resonator. L is the separation between the two resonator mirrors. You see that we shall be using this geometry in order to do our calculations. And you see that here we have stated the field can be calculated if the complex field parameter Q is known. So we have to find the value of Q for this geometry. To find Q, we use the equivalent lens guide structure shown in figure 2. This gives a look of general class of resonators consisting of two plane mirrors and containing an and containing an optical element consisting of two lenses of a focal length f1 is equal to r1 and f2 is equal to r2. So you see that we shall be using this geometry in order to find the complex radius of curvature q. Let us assume that the single pass propagation matrix from mirror 1 to mirror 2 is separated by the matrix is represented by the matrix elements A1, B1, C1, D1. The round trip matrix A, B, C, D is thus found as given. First of all, I am going to let you know what is the matrix which has the elements A1, B1, C1 and D1. This is the matrix which represents the propagation from mirror 1 to mirror 2. So we are now going to calculate the round trip matrix ABCD. So this ABCD matrix will start from mirror 1, then it will move, then the propagation will move towards mirror 2, and then from mirror 2 the propagation will go backward towards the mirror 1, forming a complete one round trip. And you see that just after the mirror 1, from just after the mirror 1 to just before the mirror 2, the propagation will be defined by the matrix A1 having the elements A1, B1, C1 and D1. So let's form the round trip matrix ABCD. Consider the matrix, this ABCD matrix is equal to the product of four matrices. So the rightmost matrix is 1, 0, 0, 1, which is actually the reflection matrix of the mirror M1. So after the mirror M1, the light will propagate from mirror M1 to the mirror M2. And for that one, we have the matrix represented by A1, B1, C1 and D1. It excludes mirror 1 and it excludes mirror 2. And it gives you the propagation for the rest of the region. That is the region just after the mirror 1 and the region just before the mirror 2. That is represented by the matrix A1, B1, C1 and D1. And then when the propagation will reach, when the field will reach the mirror M2, it will be reflected back. And the reflection matrix 1, 0, 0, 1 will appear. So this matrix is due to the second mirror. And after this reflection, the field will travel back towards the mirror towards the mirror M1. And just before the mirror M1, the matrix will represent the field propagation backward from mirror 2 towards mirror 1. And you see that here, this is the matrix containing the same elements but in different orders. That is the element in the position A1 has been replaced by the element in the position D1. That is, we have interchanged the positions of A1 and D1. The rest of the positions, that is the position of B1 and C1 is the same. And you know that when we construct a matrix for the reverse path, then of course we need to interchange the locations of the A1 element with the D1 element. The rest of the systems will be the same. So you see that the product of these four matrices will give you the round trip matrix of the system. So you see that what we did is that we just started over a field just in front of the mirror M1, and the light is moving towards the mirror M1. So when the field just in front of the mirror M1 will move towards the mirror M1, it will be reflected by the mirror M1. So we have the reflection matrix on the rightmost side, which is 1, 0, 0, 1. And you know that after this mirror, the light will propagate towards the mirror 2. And in this region, the light will travel, for example, in the region after the mirror 1 and just before the mirror 2, the propagation of the field is governed by the matrix which is one A1, B1, C1 and D1. And this matrix will provide you the field just before the mirror 2, and then the field or the rays will hit the mirror 2 and will be reflected back. So the reflection will be carried out by the third matrix which is 1001, and then the light will or the field will travel from just after the mirror 2 to just before the mirror 1, and that is governed by the matrix D1, B1, C1 and A1. And the product of these four matrices will then give you the ABCD matrix for the round trip, where 1001 is the matrix of a plane mirror, and A1, B1, C1, D1 is the matrix that covers the propagation just before the lens 1 to just after the lens 2. And D1, B1, C1, A1 is the matrix for the return journey, which is obtained by interchanging A1 and D1 in the forward journey matrix. So the simplified result after multiplication of the four matrices is given. So ABCD is equal to, on the right hand side we have 2A1 D1 minus 1. The next element is 2B1 D1. In the second row we have 2A1 C1, and the second element of the second row is 2A1 D1 minus 1. Here you can see that the element in the position A and the element in the position D, they are equal to each other, which is equal to 2A1 D1 minus 1. So it means that in the matrix on the left hand side we can set A is equal to D, which is obvious. And you know that ABCD is a matrix for the one round trip. Now you see that we have encountered the equation that is I am just talking about CQ square plus D minus A multiplied by Q minus B is equal to 0. This is the matrix we have already discussed in slide number 86. And this matrix, so let me, if possible, I would like to explain this matrix right now. You know that this matrix is obtained from this matrix, which is Q2 is equal to A2 Q1 plus B2 C2. So you see that for the matrix, since we are using the elements A1, B1, C1, and D1, so Q2 will be in our case Q2 will be equal to A1 Q1 plus B1 divided by C1 into Q1 plus D1. So you see that if you set Q2 is equal to Q and set Q1 is equal to Q, that is you set both Q1 and Q2 equal to Q, then you see that this matrix, this equation will give you an equation which is quadratic in Q. And you know that when we set Q1 is equal to Q2 is equal to some value Q, it means that the field, it means that the radius of curvature, Q1 is the complex radius of curvature at the initial position, and Q2 is the complex radius of curvature after a one round trip. And if the radius of curvature of after a one round trip is the same as the initial radii of curvature, then it means that the field will repeat itself, which means that the resonator is stable. So using the stability of the resonator, using the property of the stability of the resonator, we can set Q2 is equal to Q1 is equal to Q. So this will form a quadratic equation in Q. So that's why I have written a quadratic equation over here, CQ square plus D minus A into Q minus B. And here I am using the matrix elements A, B, C, D. That is, I am talking about this matrix. So in the equation that I have just shown, you can replace A2, B2, C2, D2 in that equation by A, B, C, D. And then you can set Q2 is equal to Q1 is equal to Q. And then solving that equation, because that is a quadratic in Q, so we have CQ square plus D minus 1 into Q minus B is equal to 0. But you know that now just we have found that A is equal to D. So setting A is equal to D over here, So b minus a will become equal to 0, and then we are left with c into q square minus b is equal to 0. For this equation, if you consult slide number 86, you can find this equation in slide number 86. And thus, using a is equal to d in this quadratic equation, we have c q square minus b is equal to 0. And solving this for the value of q and assigning that one to the value of q1, we can set that q1 is equal to q is equal to iota times square root of minus b over c. And you know that the value of b and c can be obtained from this matrix. So this is the value of b, which is 2b1 d1, and this is the value of c, which is 2a1 c1. So replacing b and c with the values from the matrix on the right hand side of equation number 1, we obtain this equation as shown in 2. So q1 is equal to iota times the square root of minus b1 d1 over a1 c1. But you know that to make q1 complex, by definition the q1, which is the complex radius of curvature, has to be complex quantity. It should not have any real part. It should be purely complex. And you know that from equation number 2, it follows that in order to make a q1 to be really complex, we want that b1 d1 over c over a1 and c1 must be a negative quantity, so that the negative sign will cancel out the negative sign present in the square root sign, so that the two negative sign will cancel out, and the square root will contain a term which will be positive. But you know that the square root is multiplied by iota outside, so q1 will be purely a complex quantity in that case. So now to make a q1 complex, b1 d1 over a1 c1 should be less than 0, which assures q1 to be purely imaginary. That is, q1 has no real part. That is 1 over r1 is equal to 1 over infinity is equal to 0. So let me show you. You see that this is a condition that we have also discussed in slide number 86. But you know that, let me remind you that how we can obtain this q1 and how we can set 1 over r1 is equal to 1 over infinity is equal to 0. So I hope that I can find out this equation for example. Over this is the equation. So here you can set this q is equal to q1, this r is equal to r1, and this w is equal to w1. So this equation will remain valid for 1 over q1, for 1 over r1, for 1 over w1. Similarly, this equation will also be applicable if we choose 1 over q2 is equal to 1 over r2 is equal to something over w2. So now I am talking about q1. So for that one, if you set r1 is equal to infinity over here, 1 over r1, 1 over r infinity is equal to 0. And then you are left with 1 over q1 is equal to minus iota times lambda over pi w1 square. Okay, so that's why we have set 1 over r1 is equal to 1 over infinity is equal to 0. Because we want q1 to be completely a complex quantity, purely a complex quantity. So the real part must be 0. That's why we have set r1 goes to infinity. You know that when you set r1 to infinity, what does that mean? That is, the equipath surface just in front of the mirror 1 is a plane surface, because r1 infinity means that the surface, that the equiphase surface just in front of the mirror 1 is a plane. That is, a plane wave front is incident on the lens 1 from the left, because the radius of curvature is infinitely large, which means that the wave front which is incident on the lens 1 from the mirror 1 is actually a plane wave front. This means that the wave front after the lens 1 has a radius of curvature equal to the focal length f1 of the lens. Because a plane wave is incident on the lens, so the lens will converge that beam, that plane wave front after it propagates through the lens, and then of course the radius of curvature will be equal to the focal length f1 of the lens. Now Q1 may be regarded as the complex beam parameter for the beam propagation from mirror 1 to mirror 2. To find the complex beam parameter for the beam propagation from mirror 2 to mirror 1, we can interchange A1 and D1 in equation number 2. So you see that I have derived equation number 2. If you interchange A1 with D1 or D1 with A1, you will get a parameter which is the parameter 2, which represents the complex radius of curvature of the field when it is reflected off the mirror 2 and moving towards the mirror 1. So Q2 can directly be written from equation number 2. So Q is equal to iota times, and then the square root contains minus A1 B1 over C1 and D1. Because I have replaced D1 with A1 and A1 with D1 in equation number 2. To establish that Q2 is purely imaginary and has no real part, that is 1 over R2 is equal to 1 over infinity is equal to 0. That is the plane wave front incident on the lens 2 is a plane wave front, that is quasi phase surface just in front of the mirror 2 is plane. Then you know that we can write this Q2 in a slightly modified form. So Q2 is equal to iota times square root of minus A1 B1 over C1 over D1. This can be written as iota times square root of minus, then multiplied by the square of A1 over D1, and then multiplied by B1 over D1 over C over A1 over C1. We have actually reproduced this term A1 D1 over A1 C1 because this term was present in the definition of Q1. B1 D1 over A1 C1. That's why I have reproduced this term by introducing an extra term A1 over D1 whole square. But you know that we have already set up the condition that B1 D1 over A1 multiplied by C1 should be less than 0. You know that the square root contains a negative sign, it contains a squared term, and it contains B1 D1 over A1 and C1. So if B1 D1 over A1 C1 is less than 0, it means it is a negative quantity. Then the negative sign will cancel the negative sign within the square root, and so the square root then will contain only positive quantity, which means that Q2 then will be purely a complex quantity, and which means that a plane wave front will be produced after reflection from the mirror 2. Thus, plane wave front is incident on the lens 2 from the mirror 2, and the radius of curvature of the beam from lens 2 just after it, that is propagating towards 1, will be equal to F2. That is, radius of curvature R2 will be equal to F2, which is the focal length of the lens 2. Field corresponding to a given eigenmode is composed of superposition of traveling waves that exist in the resonator. The matrix A1, B1, C1, D1 is obtained by writing the product of matrices in the order reverse to the order that the components within that resonator are propagated. You see that earlier we have said that A1, B1, C1 and D1 is a matrix for one pass. That is, it is a matrix that takes care of the propagation just after the mirror 1 and just before the mirror 2. And similarly, just after the mirror 2 and just before the mirror 1, when A1 and D1 are interchanged. So now I am writing the matrix A1, B1, C1, D1 for the which takes care of the propagation from the of the field just after the mirror 1 and just before the mirror 2. For that one, I am writing out. You see that on the right hand side, I am writing down the matrix for the lens 1, which is 1, 0, minus 1 over R1 and 1. And then the light will travel a distance equal to L within the resonator. which I like to show you, that this is the length L. The light after the passing through the lens 1 will travel the distance in free space equal to L. And for that one, we have a matrix that is given over here. That is 1L01. This is the matrix for the free space propagation covering a distance, geometric distance equal to L. And then the light will pass through the lens 2. And then we have the matrix for the lens 2, which is 1, 0, minus 1 over R2 and 1. So the matrix of the lens 1, then the matrix for the free space propagation, then the matrix of the lens 2. So multiplication of all these together, the three matrices will give you the matrix which is shown over here, which is equal to, the first element is 1 minus L over R1. R1, the second element is equal to L, the third element is equal to minus 1 over R2. Within the parentheses, we have 1 minus L over R1 plus 1 over R1, and then the second element of the second row is 1 minus L over R2. And you know that, of course, this is the matrix that takes care of the propagation after the mirror 1 and before the mirror 2. And this can be represented in terms of the G parameters, that is in the parameters G1 and G2, where G1 is equal to 1 minus L over R1 and G2 will be equal to 1 minus L over R2. So expanding this term over here and introducing the parameters G1 and G2, we have the matrix A1, B1, C1, D1 is equal to G1, L minus 1 minus G1, G2 over capital L, and then G2, as shown in equation number 4. So this is the representation of the A1, B1, C1, D1 matrix in terms of G parameters. To find the beam waist W1, we use the beam propagation parameter Q for the forward journey in terms of the A1, B1, C1, D1 matrix elements. As you see that we have already obtained Q is equal to iota times minus B1 D1 over A1 C1, the square root of this whole quantity. And we can compare it with Q obtained from this relationship. You see that in this relationship we have to set the value of R goes to infinity, that is R1 goes to infinity. So we have 1 over infinity equal to 0. So that the Q should have only a complex variable, only purely a complex quantity. And then you see that solving this one, we have 1 over Q of Z is equal to minus iota times lambda over pi W square of Z. And from here you can get the value of Q, which is equal to minus iota into pi W1 square over lambda. So if you write Q1, you can write W1. So I can write Q1 over here instead Q. So Q1 is equal to iota times into pi W1 square over lambda. And this is also Q1 because it is the complex radius of curvature at the initial location. That is at the location of the mirror 1. So we have this Q1, we have this Q1 also, and then you can equate the two Q1 or equivalently the two Qs together to get this relationship. Using the values of the matrix elements A1, B1, C1, D1, which we have derived over here, A1, B1, C1, and D1 matrix, the elements are completely known in terms of the G parameters. If you substitute if you substitute the values of B1, D1, A1, and C1 from the above equation, then we have W1, that is the radius of the beam waist. W1 is equal to square root of L lambda divided by pi multiplied by G2 over G1 into 1 minus G1 G2 whole term raised to power 1 over 4. So this is what we have found W1. To find the beam waist W2, we use the complex beam parameter for the propagation of the field from mirror 2 towards mirror 1, which is from equation number 3 is. So you see that this is what we have obtained Q2. And let me show you that we have obtained Q2 earlier. For example, this is Q2, and Q2 was obtained from Q1 just by interchanging the positions of the A element with the D1 element. So A1 and D1 are interchanged to get the position, to get the value of Q2. And in the Q2, we can set up the values of A1, B1, and C1 and D1 from this matrix. And then we have the value of Q2 is equal to here I times into the square root of minus A1, B1 over C1 and D1. And now we can compare it with the Q2, which can be obtained from a relationship similar to this one, where you can have 1 over Q2 is equal to 1 over R2 minus iota lambda over pi W2 square. So here you can set R goes to infinity so that you can have only Q as a complex quantity, purely complex quantity. When you set R2 goes to infinity, it means that you are talking about a plane wave front at the location of the mirror 2. So these are the two values of Q. If you equate these two values of Q and represent and substitute the values of A1, B1, and C1 and D1 from this matrix in terms of the G1, G2 parameters, you can obtain W2 is equal to square root of L times lambda divided by pi, and then G1 over G2 multiplied by 1 minus G1, G2 whole raised to power 1 over 4. So this is the W2. So you see that we have found W1 and we have found W2. That is the beam waist at the location of the mirror 1 and at the location of the mirror 2. But now we have to find the value of the W0 value, that is the beam waist within the resonator. But you know that its location is not known. If the two mirrors are identical, then it will be located in the center of the cavity. But you know that if the R1 and R2 are not equal, it could be located before the center of the cavity or after the center of the cavity. So we have to find two things about this beam waist. One is the location, that where this beam waist is existing, and the second is that we have to find out the radius of this beam spot over here, which is W0, because W0 is the diameter of the beam or the diameter of the laser spot within the resonator. So for that one, we have to do the calculations for W0. To find the beam waist W0 within the cavity, we proceed as follows. A Gaussian beam of spot size W1 with a plane wave front enters the lens 1. This is what we know. You see that we have found the spot size radius W1 at the location of the lens 1 or the mirror 1. And you know that there the wavefront was a plane wavefront. So a Gaussian beam of spot size radius W1 with a plane wavefront enters the lens 1. That is, the beam waist is located at the lens 1. The beam waist position after the lens 1 and its spot size W0 need to be calculated. Let's denote the transmission matrix of the lens followed by a free space distance Z by A2, B2, C2, D2, which is found from. You see that here we need to find another matrix A2, B2, C2, and D2 for a general distance D for a general distance Z after the lens, because Z is unknown, because we do not know the location of the spot size located, that is the beam waist W0, that is the location of the W0 position within the resonator is unknown, and we are assuming that it is at a distance Z from the lens. So we want to find out the matrix for that region. So A2, B2, and C2 and D2 is the matrix for such a region, which consists of two matrices. One is the matrix, this one, 1, 0, minus 1 over F1 is equal to 1 minus 1 over F1 and 1. This is the matrix for the lens 1. And then the light after the matrix, after the lens 1 will travel a distance Z in free space, because we are assuming that the beam waist spot W0 exists at a distance Z from the lens 1. So that's why we are using this free space propagation for a distance z, and the matrix is 1 z 0 1. The multiplication of these two matrices will give you 1 minus z over f1, then z, then minus 1 over f1, then 1, as shown in equation number 7. So if we could determine the value of z in this equation, then of course the position of the beam waist will be known to us. The complex beam parameter Q2 after the length 1 and the free space distance z can be related with the parameter Q1. So we are assuming that Q2 is the parameter at the location of the beam waist W0, which is related to the parameter Q1 at the position of the lens through the parameters of the matrix, which is A2, B2, C2, and D2 matrix. So Q2 is equal to A2 times Q1 plus D2 divided by C2 times Q1 plus D2, where Q1 is the complex radius of curvature at the lens position and Q2 is the complex radius of curvature at the beam waist position within the resonator, where Q1 being purely imaginary, because this is what we have already discussed, that Q1 is being a purely imaginary, and 1 over R1 is equal to 1 over infinity is equal to 0. So 1 over Q1 is equal to 1 over R1 minus iota times lambda over pi W1 square. So you see that here, of course, you can set 1 over R1 is equal to 0, and you have 1 over Q1 is equal to minus iota times lambda over pi W1 square. From here, you can get the value of Q1. Q1 is equal to iota times of pi W1 square over lambda. Or Q1 can be written as minus, or sorry, the Q1 can now be written as Q1 is equal to iota times pi W1 square over lambda. This is what we have derived, for example, over here. But we can set that one is equal to iota times ZR1. Because Q1 is of course the radius of curvature, complex radius of curvature, we can set its value equal to iota times ZR1, where ZR1 is a real distance because we have separated iota from here, as shown in equation number 9. But you know that ZR1 is equal to pi. So where ZR1 is equal to pi W1 square over lambda, because in the writing equation number 9, the rightmost side part of the equation is obtained by setting ZR1 is equal to pi W1 square over lambda. Substituting metric elements A2, B2, C2, D2 in and Q1 in equation number 8, we obtain. So you see that we have equation number 2. We can substitute the values of A2, B2, C2, and D2 from this equation number 7, and we can also substitute the value of Q1 over here in terms of the parameter ZR1. So if you substitute these two values over here and rearrange the terms for Q2, we get Q2 is equal to as shown in equation number 11. So now Q2 has two parts. It has an imaginary part with the iota multiplication with that one, and then the other part is completely real. Now you see that for Q2 to be purely imaginary, the real part of Q2 in equation number 11 must be 0. So we are setting the real part equal to 0, and from that part we are getting numerator z minus zr1 square over f1, and then within the parentheses we have a 1 minus z over f1 equal to 0. That is the numerator of the real part in equation number 11 has to be 0, because we want Q2 to be purely imaginary. So solving this one, we can find out the value of z. So z is equal to f1 divided by 1 plus square of f1 divided by zr1. So you see that in this equation, all the quantities on the right hand side are known. So it means the value of z is known. It means the value of the beam waist within the resonator is known. And you know that this z is the distance from the lens 1. So the position of the beam waist within the resonator from the location of the lens 1 is known, which is given over here. This value of z can be identified as the distance from the lens 1 where the minimum spot size occurs and can be denoted by Zm, that is, so this z can be declared as Zm because this corresponds to the distance where the beam spot becomes has a minimum diameter, that is where the beam waist exists, and due to the minimum beam spot there we are denoting the corresponding distance by z minimum, that is Zm is equal to f1 over 1 plus square of f1 over zr1 as shown in equation number 12. Thus we have, so you see that we have set the real part in equation number 11 to be 0, and now q2 being a complex quantity has only this term with it. So q2 can be written now as, which is purely a complex quantity. So q2 is equal to iota, q2 is equal to iota times zr1 over 1 plus square of zr1 over f1 as in equation number 13, which is only the imaginary part of equation number 11 because the real part is 0. But you know that q2 is also given by q2 is equal to iota times pi w naught square over lambda, because this is q naught that is at the location of the beam waist w naught, and you know that we can use this equation. For example, you can use this equation to find out the value of q, because you need to set 1 over r equal to infinity. So this becomes 0 because we want q to be complex quantity, and then you can find out the value of q. So for that q, you need to set w naught over here, because this q will correspond to the complex radius of curvature where the beam waist w naught exists. So set w naught over here and then set q2 there. So we have q naught is equal to iota into pi w naught square over lambda in equation number 14. So equating q2 from equation number 13 and 14, we get w naught is equal to w1 over square root of 1 plus pi w1 square over lambda f1, the whole square of that quantity. So this is equation number 15, and it gives you the beam waist in terms of the radius of the spot within the resonator in terms of w1. Substituting w1 from equation number 5 and replacing f1 by r1 in the simplification process, replacing 1 minus l over r1 by g1, because we want to introduce the g1 parameters. So the final result we obtain is given in equation number 16. So w naught is equal to square root of lambda L times lambda divided by pi, and then we have g1 g2 within the parentheses we have 1 minus g1 g2 divided by g1 plus g2 minus 2 times g1 g2 whole square, and then the whole term has a power equal to 1 over 4. In symmetric resonators, R1 is equal to R2 is equal to R, and G1 is equal to G2 is equal to G, because all these quantities are equal to 1 minus L over R. And the above results now take the form. Then W1 will be equal to W2 is equal to W is equal to square root of lambda L times lambda divided by pi, and then we have 1 minus g square whole raised to power 1 over 4, and for w naught we have square root of lambda times L divided by pi, and then we have 1 plus g divided by 4 times into 1 minus g whole term raised to power 1 over 4. So you see that we have found the radii of curvature, we have found the beam spots, we have found the beam wastes at the mirror 1, at the mirror 2, and in the center. So the beam waist at the 3 different positions in terms of the G parameters and other parameters of the cavity have been found. For example, the separation of the cavity in terms of L and the wavelength of the light. So this completes our answer. And this is the end of slide number 87.